All right, everyone. So here it is, a really quick explanation of problem 2A that we looked at together. This is going to set you up to complete 2B as well. And I'll make a quick distinction about the strategy. But here it is, kind of what I was trying to get us to logic through, I guess. Question 2A. What is the total energy required to bike 2.5 miles at an average velocity of 6.7 meters per second? Assume the person and the bike weight 80 kilograms. And right off the bat, let me just start highlighting the stuff that we are given, values that will be important to incorporating the total energy. We'll get to the total. If your intuition is telling us we have to do something different because there's something else doing, awesome. Let's build on what we already know and then get to that, second part, that total part in a second. So we've been looking at kinetic energy this whole time. The energy, the difference between this and the potential energy is that this requires some type of velocity. 1/2 mv squared, where m is mass, v is velocity. And what is our mass? 80 kilograms over here is what I see. So I'm going to go put 80 kilograms. Velocity is the 6.7 meters per second, right? And again, this is the same thing as multiplying two 6.7s. I'm going to go ahead and square it in my own calculator, right? So 6.7 squared gives me 44.89. I'm just going to write it down so that you're following along, but you can definitely go ahead and write it in your own, you can calculate all of this together to get that result at the end. M squared over s squared, we're squaring that whole thing. 1/2 times 80. I'm going to go ahead and jump there too. That should be 40 kilograms, right? That's half of that. And 40 times 44, multiplying that here, that should be at around 1795.6 is what I'm getting in total. Kilograms times meters squared over seconds squared, our unit for energy. This is our kinetic energy for this car. But as I said, right, if you started pedaling at this speed and then you suddenly stop throughout the journey that you're traveling, you're going to slow down until you completely stop. We need a little bit of energy each mile just to sustain this velocity, right? So this is how much you're going to take to even get to that speed. But we need to account for now this second part to complete those 2.5 miles, right? So let's put this under part 1. I'm going to go ahead and write here part 2, that we need to account for how to actually keep the speed throughout the whole journey. So I'm going to go ahead and write that there is 25 kg m squared over s squared. This is telling us this is some quantity of energy needed to sustain this velocity per mile. So this is all for 1 mile. It's now just a matter of multiplying by the quantity of miles that we have, right? I'm just going to write it here, but you can imagine that this is all per mile, right? And this would be 2.5 miles. Let me go ahead and write that explicitly here. 2.5 miles. Whoa. Which means that these will cancel out. That's why we multiply, so that these cancel out and do it there. If your intuition is just 2.5 times 2.5, which is, 25 times 2.5, which is a quantity of miles, that also works, right? That also makes sense. 25, 2.5 should give us about 62.5 kg m squared over s squared. 62.5 kg m squared over s squared. Quick review. We calculated how much energy it would take for us to even get to this speed, how much energy is required, and we also calculated how much energy we need per mile to sustain it. Multiply that times the amount of miles, it gives us our total energy for the trip, right? For the whole 2.5 mile trip. So now we have this quantity and this quantity to account for the whole trip. It's now just a matter of adding them together. 1795.6 kg m squared over s squared plus the 62.5 kg m squared over s squared. Plugging that into my own calculator right now. 1795.6 should give us, let me know what y'all get, right? kg m squared over s squared should give us 1858.1 kg m squared over s squared as our final total energy, right? Accounting for not only the velocity but also how much we need to sustain that velocity. Okay, so hopefully that makes sense. It's a one additional step that isn't hopefully mathematically too challenging, but it just accounts for, you know, applying it for a longer example with this 2.5 miles. That is the one variable that was thrown, that was new, we haven't seen it before, and I tried to make the math simple so that you wouldn't have to stress too much about what exactly we're doing. The one thing I will note for 2.2b is that it is no longer per mile, it's for the whole journey. So that should make things even simpler for you when you're calculating on one hand the KE and on the other hand to sustain that KE. So hope that's helpful, y'all. Thank you for all your work this week.